All right, let's just dive right into this. Welcome to The Explainer. Today, we're unpacking some absolutely brilliant research from theoretical physicist Dr. Ahmad Rihan. And honestly, his work completely flips how we look at something we literally take for granted every single day: classical electromagnetism. We're going to break down this pretty heavy physics into a visually clear journey that might just change how you see the space around you. So, for over 150 years, James Clerk Maxwell's equations have been put on this pedestal, right? They're revered for their perfect mathematical elegance. They are the absolute bedrock of modern physics. But there's a catch. We're almost always taught these equations in the context of a completely empty vacuum. We're told to picture light and magnetic fields just traveling through this passive, entirely empty void. But what if the environment they operate in isn't just some empty stage? What if it's actually an active player in the whole thing? That's exactly the question Dr. Rihan is asking. So today, we're going to see what happens when we shift our focus from a boring, passive vacuum to a dynamic, active environment. What actually happens when the space around us is a real participant in this electromagnetic dance? To get there, here's our roadmap. We'll start with the perfection of Maxwell. Meet the active environment. Look at a symmetry-inspired tweak. Explore ripples in the wave. Figure out how conductors actually work, and finally, wrap up with engineering the future. Let's get to it. Section 1. The perfection of Maxwell, the vacuum baseline. If you've ever opened a standard physics textbook, you've seen this: permittivity and permeability. Basically, the measures of how space resists the formation of electric and magnetic fields, well, they're treated as these rigid, totally unchanging constants of free space, epsilon naught and mu naught. In the standard baseline physics, they're just numbers you plug into an equation. They never change and they never react. Section 2. Meet the active environment, the spongy medium. Now, check out the contrast here. When we step out of a theoretical vacuum and into a real material medium, like glass, water, or even just the immediate environment around a wire, we actually replace that rigid constant with a variable epsilon. This represents the relative environmental permittivity. And this is a huge deal because it's dynamic. It describes the environment's specific ability to store electric energy and actively polarize whenever there's a charge. This table brilliantly illustrates what happens when that environmental permittivity cranks up. A high-permittivity environment acts exactly like a sponge. Based on Gauss's law, it absorbs and screens the electric field, so the actual E field decreases. But at the exact same time, via Ampere's law, it acts like a trampoline that amplifies magnetic field generation. So changing electric field in this kind of environment produces a way stronger magnetic field. And while all this is happening, the overall speed of the electromagnetic waves slows down. So the medium isn't just sitting there, it's actively dictating the terms of how energy transfers. Section 3. A symmetry-inspired tweak. Rebalancing the math. To make the math perfectly symmetrical, Dr. Rihan suggests this really elegant phenomenological adjustment. See, Ampere's law already includes environmental permittivity to account for displacement current. So Dr. Rihan says, why not explicitly include that same environmental permittivity factor on the induction side of Faraday's law too? You basically weight the electric field by epsilon before taking the curl. It creates this absolutely beautiful symmetry between electricity and magnetism when you look at it through the lens of the medium. By following these mathematical steps, starting with that modified Faraday's law, taking the curl, and substituting it right into Ampere's law, we derive a modified wave equation. And what's crazy here is that the mathematical form of the wave equation doesn't actually change, meaning the wave speed doesn't break standard physics at all. But the interpretation completely flips. It reveals a much deeper truth about how energy is partitioned. The back reaction of a changing magnetic field inducing an electric field, it's now explicitly weighted by the environment itself. Section 4. Ripples in the wave. Inhomogeneous media. Okay, so when the environment's permittivity varies in space, what we call an inhomogeneous medium, these brand new extra gradient terms suddenly pop up in the math. What does that actually mean for us? Well, it means the environment actively scatters and guides electromagnetic waves completely on its own without needing a physical wall or boundary. A smoothly varying permittivity produces optical effects like mirages, or acts like a waveguide where the space itself becomes a channel for the energy. The space is literally steering the wave. How cool is that? Section 5. How conductors actually work. The Faraday limbs. Let's think about the everyday copper wires running through your house. Normally, we just picture conductors as empty pipes for electrons to flow through, right? Well, Dr. Rihan argues they're actually more like high-permittivity Faraday limbs. As static charge builds up,
It actively increases the local permittivity. This higher permittivity screens the internal electric field, driving it all the way down to zero inside a perfect conductor, while simultaneously supercharging the magnetic power transmission on the outside. So the energy isn't just flowing inside the wire like water in a hose, it's being guided around the outside by a highly reactive environment.
This is a total game changer for how we understand electricity. Look at the left side here. The standard view usually dumbs down voltage as just a mechanical push of particles. But look over on the right. In Dr. Rian's framework, voltage emerges as a direct consequence of dynamic permittivity gradients. When charge accumulates, the local permittivity shifts, which allows charges to redistribute way more effectively. So voltage isn't just a physical shove. It's the environment itself shifting its capacity to store energy, pulling and guiding the charge along with it. Section 6. Engineering the future. The power of epsilon. If we know for a fact that permittivity actively guides and amplifies fields, we can actually engineer it. We're talking about creating tunable dielectrics and metamaterials that can dynamically control how waves propagate. Think about smarter, way more efficient high-voltage power lines that use specific geometric and material permittivity to perfectly manage corona discharge, or even next-generation photonics and high-frequency energy harvesting systems that can tune field interactions dynamically, stuff the old standard vacuum formulas could never have predicted. We are literally learning how to play the environment like an instrument. Which leaves us with a pretty profound realization. We've just seen how Dr. Rian's framework takes a 150-year-old equation and breathes total dynamic life back into it, just by giving the environment a voice. So if the so-called empty space around a wire is actually actively dancing with electromagnetic fields to drive energy forward, what other invisible interactions around us are just waiting to be unlocked and engineered? Thanks so much for joining me on this explainer. Keep questioning the baseline, and I'll catch you next time.